Now in this video we're going to be looking through an example with balanced forces with this picture over here. We have two books lying on top of each other on a table on the ground. Okay, so now we have our model over here and we're gonna make up some numbers. Oh, actually, what the heck? Let's make things a little more interesting, okay? Forget these books. Gonna do a new thing over here. We're gonna spice things up a bit by saying that instead of those books, we now have three animals stacked onto each other. We have a blue penguin stacked onto a red dinosaur on a green dinosaur. So this would have been a table previously, and these two would have been books. So same model, but I guess hopefully a little more interesting. We're going to start with the penguin first, because he's on top, he's the easiest. A penguin is really light. It has a mass of 2 kilograms. So that must mean its weight, you can just calculate with our formula. I might start skipping units later on, okay? Hope you don't mind. And so its weight is 19.62 newtons. Of course, it also has a normal force, right? The normal force is from the exerted by the red dinosaur on it. Now in this case, it is a normal force, but I'm going to call it the force exerted by red on blue. And that's a good reason why I'm calling it that. You find out later. That's red on blue. And that balances out the weight force, so you'll have the same magnitude, or else the penguin will fall down. By the way, hopefully you got this much, that we've established a coordinate system as going upwards to be positive. Okay, and that was for the penguin. Now, we're going to move on to the red dinosaur. This guy's a little trickier. Let's just say he has a mass of 3 kilograms. And so naturally the weight force can be calculated pretty easily. And don't forget, we also have the penguin's weight exerting a force on the red dinosaur. Blue's exerting a force on red. Now, conceptually, here comes the really tricky part. What do we call that force? What do we call this force? Many students intuitively just say it's called the weight force, because it seems to make sense, right? But conceptually it's not correct. And some instructors actually trick students about this concept. My professor even used to call it the force due to the weight. But why isn't it called just the weight force? What's the difference? Remember, the weight of an object is the force of gravity acting on that object. So the weight of this blue penguin over here can only act on the blue penguin. It cannot act on the red dinosaur. So what is that force? What is this guy, if it's not weight? Well, it's actually a normal force. You can think of it as the top surface on which the red dinosaur is lying on. And in this case, it's the blue penguin's butt. Now, in fact, since you know about Newton's third law, this normal force, actually exerted by the penguin on the dinosaur, is actually the action-reaction pair of the normal force that the dinosaur exerts on the penguin. But in this case, is a force exerted by blue on red, with the opposite directions and the same magnitude. The rest is fairly straightforward. We have the bottom green dinosaur exerting a normal force on the red dinosaur to balance out both its weight and a force due to the weight of the penguin. And once again, instead of calling it a normal force going upwards, we're going to be calling it the force exerted by green on red. The magnitude is equal to the addition of these two, which is 49.05. Now all this might be enough for some of you, and you can stop here. But if you really want to torture yourself, why don't we also draw the free body diagram for the bottom dinosaur, the green one, just for fun. This guy's a bit heavier, it has a mass of 20 kilograms. And I calculated that weight beforehand, so trust me. Now what about the force exerted by the red dinosaur on the green? Well, that force is going to be equal to red exerting its force due to the weight on green, plus the force exerted by blue through red on green as well, right? It's really less confusing than I'm making it out to be, because the force exerted by red on green is yet another case of action-reaction forces. In this case, the reaction force is the force exerted by green on red, right over here. Now the rest is really simple. We're left with the normal force, or in this case we can even call it the force exerted by the Earth on the green dinosaur. And that's going to balance out the other two forces. So the magnitude would be the addition, right? And we have... Remember this one now. Just hold on to that for a sec. If there are some of those Super Saiyans out there, I'm going to show you a shortcut to problems like these. Let's say you don't want to find all the other forces, all these over here, and all we want to know is the normal force acting on the green dinosaur itself. But look, oh wow, there's so many effects of all these other guys acting on it, and oh, this gets all messed up, right? Well, all we have to do, and this is really simple, is to pretend that all three of these animals is one big animal. Something like that. So it becomes a composite object, essentially. This composite object over here is going to have a mass that is equivalent to all three objects added together. That's 23 plus 2. That's 25 in total. It will have a weight of 245.25. And that would be balanced out by a normal force on the ground of the same amount. And voila! That's the same result as what we got over here by breaking it down into essentially its component animals, right? So this giant hybrid animal, this giant hybrid object, having the mass of all three objects, will give us the same result we're looking for. A lot easier, eh? So I'm hoping you learned something new in all this, especially regarding the nature of the normal force. Alright, enough of that.